Okay, so in the last video, we're going to kind of put the whole thing together, and we're going to look at, graphically speaking, what does it look like as you take, let's say, for example, a solid, and you keep pumping energy into it. You keep adding energy into it or exchanging energy with it until eventually it starts to melt, and then eventually it completely melts to become a liquid, and then the liquid, we continue to put energy in, the liquid is heating up, and then the liquid eventually it starts to turn into a gas. It begins to vaporize, and then eventually it's completely vaporized, and then finally it's in the form of a gas, and we continue to keep putting energy into it. So we're going to look at graphical representation, and we'll look at it in basically two ways at the same time. And I am specifically going to look at so this specific graph will be for water. That's one of the common substances we're going to look at. And I'm going to make an assumption. I'm going to assume a unit mass. That is to say, I'm going to assume there's 1 kilogram of water. So we're going to take 1 kilogram of water in its frozen form, ice. We're going to start it at its absolute lowest temperature, which is 0 degrees Kelvin, and we're just going to continue to raise the temperature of this thing until eventually we have it steam, and we'll just continue to increase the temperature of that steam. So on the left axis, so on the vertical axis, this will be the temperature, and this will be in kelvins. So we will actually start at 0 kelvins. That's the lowest possible temperature. And on the horizontal axis, we could pick two choices. So and it would look exactly the same either way that I did it. It's effectively the same thing. So I could either look at Q in joules, or I could look at time in seconds. I could look at time in seconds for a constant power. So if I assume that I just keep pumping the energy in at a constant rate, at a nice constant rate, then I could look at this graph as a function of time, and the graph will look virtually identical. So I won't put any numbers on this axis. I just really want to look at the shape of this graph and the significance of this graph. Okay, so the first thing that would happen is we would have water in its solid form, ice, and as we added energy to it, or as we allow time to go forward, pumping in energy at a constant power, then what would happen is we would see the temperature of this substance starting to rise, and it would be pretty steep. So pretty steep line. And this is the substance. In this case, we're talking about water, so this would be ice. Right? So this is the solid form of this. Now what will eventually happen is we will reach a temperature of 273 degrees. This is the melting point of ice. And at that point, you would see the line flatten out. And for a short period of time, we would have a combination of ice plus water. So water can exist in both forms at 0 degrees Celsius, as both ice or as water. And so as we continue to pump energy in, as we continue to add energy to the substance, we'll see that there's a transition from all ice, this is all ice here at this point, and at this point it would be all water. So now before we move on to taking the water and letting the water's temperature increase, we just want to real carefully think about the significance of this graph. So I'm going to pull this up a little bit and just put kind of an aside here. Just to remind you, Q is equal to MC delta T. So in this graph, if I were, for example, to take the delta T over to the other side, and again, we're going to assume for our sake that this is a unit mass, so its value would be 1, then the change in energy over the change in temperature would be, that's the definition of the specific heat capacity for a unit mass. But I don't have delta Q over delta T. I have delta T over delta Q. So as a result, if you imagine flipping these things, delta T over delta Q would be equal to not C, but 1 over C. So the slope on this graph is the inverse of the specific heat capacity. So when the specific heat capacity is very small, I get a very steep line. When this number is small, this line will be very steep. And the significance of that is that it does not take a lot of energy to change the temperature a lot. Right? The smaller the specific heat capacity, the faster the temperature will rise for the same amount of energy. So the reason why I'm bringing that up is because now we're going to turn this substance into water, and water has a very high specific heat capacity. So the significance of that is that this line will be much flatter. This is specifically for water. Specifically for water. Water has a higher specific heat capacity in its liquid form than it does in its solid form. So this is now completely water. And that water will continue to increase in temperature until it eventually reaches its boiling point at 373 degrees. And at that point, we'll see another one of the latent heats comes up. This is the latent heat of vaporization. And it will flatline, and this line will be much longer than the previous one. And the reason why this line is so much longer than this one is, just to remind you, the latent heat of fusion is only 334,000 joules per kilogram, and the latent heat of vaporization is 2,200,000 joules per kilogram. So it's going to take a lot of energy to turn that into steam, much more than it took to turn the water into, or turn the ice into water. So in this case, we have water plus steam, and eventually we'll reach a point where all water, all steam. Once we reach all steam, we're going to see the temperature start to increase now because there's no more water left. And in this case, if you think about whether this line would be steeper than the one for water or more shallow than the one for water, the specific heat capacity for steam is only about 2,000 joules per kilogram, as opposed to water, which was about 4,000 joules per kilogram. So this line is going to be much steeper. Remember, this graph, this line on this graph, is the inverse of the specific heat capacity. So a smaller specific heat capacity will result in a steeper line, meaning that the temperature will change more rapidly for a given amount of energy. So this guy is steam. And there's really no limit to how high that this can go. Technically, stuff will start to happen when you get to a high enough temperature, but there's no more phase changes in terms of the phase changes that we've talked about. So you can see the C. Here is this is Ci. This is the latent heat of fusion. Then we have C for water, latent heat of vaporization, and the C for steam. You can kind of see why the latent heats are considered to be hidden heats, because again, on this graph, you're pumping energy in, but there's no obvious change in the temperature of the substance. So this is partially why the latent heats are referred to as latent heats, because they're kind of a hidden energy. And again, I could have done this graph as time or energy. Now, if I do it as time, it would be with the assumption that I am putting power, I'm putting energy into this thing at a constant rate. As long as I put energy in at a constant rate, this graph is going to look exactly the same as the as if I were just pumping in energy, if I was just measuring energy. The slope of the line will have a slightly different meaning, but the effect of it is basically the same.